Okay, thank you very much. We are now at 10:50 and we're ready to hand over to City Science. So if you'd like to share your screen and whoever's presenting, turn their camera on. And as with before, please put any of your questions in the chat as we go through and we'll field them at the end.
Thank you very much. Can you see that okay?
Yeah, that's great.
Fantastic. Okay, so hello, my name is Jade. I'm an energy and sustainability consultant at City Science, and I'm the project manager of this project. So welcome to a quick summary of the outputs of our feasibility study entitled AI Generative Design Tool for Low-Cost District Heating Networks. So firstly, our key objective at City Science is to build tools and provide services that enable decarbonisation at a city and national scale. We focus on the three major CO2 emitting sectors of transport, domestic and commercial. And as a landscape, between 2014 and 2019, carbon emissions in energy production have decreased by 54% and industry by 12%. However, carbon emissions from buildings have increased by 6%. This indicates that building energy decarbonisation is a significant factor in achieving net zero. A majority of the energy used in commercial and domestic buildings is expended through space heating and hot water. For domestic buildings, this contributes 75 to 80% of energy, and for commercial, it's 50 to 60%. There are two approaches for the UK to decarbonise buildings. One is to reduce the amount of energy used, and the other is to shift to low carbon heating sources. Now, the UK plans to address the shift to low carbon heating sources by scaling up the number of homes served by district heat networks. The government's 2050 target of 90 terawatt hours of heat served by heat networks per annum translates to around 6 million homes. However, our modelling suggests that at the current run rate, we will only reach 49% of this target, leaving us 3.2 million homes short. So as part of our early research, according to Hindu funding applications, we found that over the last 3 years, only 25 large-scale district heating feasibility studies have been conducted per year. And our modelling suggested that only 54% or 13 networks progressed to build. So it's clear that intervention is needed to enable the scaling of district heating at a much faster rate. And this is a statement that was repeated by the many stakeholders that we engaged during the study. So the question is, how can we increase the number of studies conducted, and how can we increase the number of studies that then progress to build? To understand the barriers to scaling and how the design processes can become faster, we started by documenting the process to understand the steps, the stakeholders involved in each of those steps, and when and how each of the participants interacts with the system. Then we designed a user-centric feedback process to ensure that we engage with at least one participant who interacts in each part of the process. So in a highly human-centric approach, we interfaced with all the organisations you can see on the screen. So this scoped government bodies, those in regulations and policy, large and small design consultancies, of course the ESC as industry advisors, manufacturers of the components themselves, ESCOs and local authorities. And the local authorities scope those who are highly engaged in district heating already, such as Islington, and those who aspire to be. So this approach gave us a comprehensive view of the pain points within the process and the pain points within the industry, and really provided feedback and validation throughout everything we produced moving forward. So each user had a different perspective on the approach that should be undertaken by us and had a unique set of requirements. And the engagement with the stakeholders consisted of one-to-one interviews, workshops, interactive feedback documents, videos, and surveys. So in our discussions with the participants about the pain points, we found that the most significant delays occur during the first two phases, which is heat mapping and master planning, and the techno-economic feasibility stage. This is why our final solution is a tool that uses AI and generative design to automate the process of district heating feasibility studies. Out of the 13 common pain points that we identified, we created a solution for our new application that solved 6 of the critical issues in the process. And these are incorrect or incomplete demand data, the many iterations and rework time needed to make the designs acceptable for all stakeholders, little incentive for developers to prove viability, competing stakeholder objectives, perceived value, and lack of access to capital because of the high perceived risks. We then produced our application design based on this user-centric requirement capture approach, which allowed us to have a single solution with the most buy-in. And the back end of the model, the back end of the tool uses a demand model, a network physics model, a generative design optimizer, and human-in-the-loop engineering, which I'll explain in a little more detail in the next slide. So the core of the application has two optimization loops running generative design. So in step one, the user inputs the details of their preferences and any constraints they may have. Then we run through the two loops. So the first is the network physical design loop, which looks at the routing of the network. And the second loop then looks at the network equipment like pipes and heat interface units. Finally, the AI generative solution options are published into the human-in-the-loop design space. Touching on the value proposition, the tool is aimed at design consultancies and local authorities. So design consultancies currently use a very manual Excel-based process, and it takes a long time to implement changes to designs. Local authorities who are engaged in district heating networks and have in-house skills will also be able to use the tool. Looking to the future, as government policies and targets place requirements for additional heat networks, it's likely that more and more local authorities will increase their capabilities and will be also able to use the tool. And in addition, if local authorities can use the tool to quickly and cost effectively determine whether a district heating network is feasible, then the requirement of a heat network, of holding a heat network in a new development can be stipulated in the contract rather than leaving the decision up to reluctant developers. So although aimed at those particular stakeholders, the tool has been designed in a way to appease the pain points from stakeholders across the board to promote a seamless process, provide detailed information early on, and provide designs that are accepted by all. So another aspect we heavily engaged with users on is the user interface prototype. So initially, a survey and discussions in stakeholder meetings informed the development of version 1, which included the key functionality of the tool. And following presenting version 1 prototype to users via various means, feedback was gathered in order to inform the version of the user interface that you're about to see. And that's currently designed as a web application. So this is still a work in process, and we will use this prototype as the basis for the solution design as part of the beta process, as every section of the application is developed to replace the mockup with the actual outputs and will continuously take feedback from users as it develops. So if we click to log in, we are taken straight to the project dashboard, which captures the workflow and projects. So we have in-progress projects that you can click on and work on, and we have submitted but not confirmed, and we have completed, so either they're being progressed to build or were unsuccessful. A tagging system allows the user to categorize the projects based on the primary technology, cost, network size, location, etc. And a filtering system allows the projects to be referenced in the future. Along the top, there are standard dashboard elements, such as the number of projects submitted, and the drop-down menu allows you to change the time period of these stats to suit company targets and reporting timelines. So if we click New Project, once we have uploaded the data, this is gone, sorry. So once we click New Project, we give the project a name and provide further details. So this includes the functionality to enable a data upload and manipulation for estimating the heat demand for both new and existing buildings, network dig and restoration costs, potential heat generation and storage locations, and so on. The tool can start with a low level of data granularity and then expand to the same model with more granular data as it becomes available as the project progresses. So we plan for integration with a number of existing tools at this point, including Thermos, the Scottish heat map, as well as Bayes' heat zoning tool, which is currently being procured for England. So once we've uploaded the data, this page captures the preference set. So that feeds into the underlying model to aid selecting and ranking the results. You can see that we have currently based this on CO2 emissions, OPEX and CAPEX. You can also drag any of the additional criteria, such as internal rate of return and net present value. The second element, which adds user input, is the constraint function. So for example, minimum and maximum number of buildings in the network, maximum heat price that are comparable to counterfactuals, and financial constraints such as payback period. So if we click Run Solution, this is where the back end of the model goes off and does its thing and uses AI generative design to set thousands of design options based on the user's preferences and constraints. And then it produces a range of optimized network designs. So the search space includes energy center locations, types, and storage options, network routing and topology, building connections, buildings retrofit scenarios, pipe selection, as well as HIU and heat meter selection. So the result is a list of scored and ranked designs that are within your constraints and optimized for your preferences. There is an option on all the pages moving forward to export the data as a CSV file and therefore integrates with the current processes that designers use. And here the sliders allow you to filter the solutions in both the parallel coordinate graph and the solution table. You can therefore evaluate which one you want to look at in more detail. And in the graph, it gives you a quick overview on how the preferences were met. So for example, the gas turbine scored well on CapEx and OpEx, but of course, scores badly on carbon emissions. So if we look at the hydrogen boiler solution in more detail as an example, we're provided with various options for a detailed analysis. So for now, if we select solution details, this opens out into a more detailed information, including KPIs that were again suggested by the user stakeholders, scorings and rankings. We can see a schematic of the network here. So this is a radial network design, and the graph here shows the Pareto front. So that's the selection of the most optimal designs of the overall solution run. So the solution we're looking at right now is here, and the graph allows us to explore the other optimized designs. So if we click to a different one, we're taken to the solution details page for that design. And within the tabs, there's a plethora of other analysis. So we have our interactive GIS map. So this was produced in the tool by the alpha phase. And this is where human in the loop element comes in. So obviously we're aware that no matter how optimized a network looks to the algorithm, there's always going to be additional considerations. AI is never going to be able to replace the engineer completely, and nor do we want it to. Our intention is that AI and human expertise can be perfectly blended to produce viable, optimized results that are far more efficient than what is done today. So this page is where the users can utilize their expertise to manually experiment with the connections, pipe storage, energy generation locations, etc., to build a network that really works. So moving to the financial analysis, this tab provides different stakeholder overviews for different contract types. So when you click the contract type, you're presented with the relevant stakeholder roles, and then you can drag the ones that you're interested in looking at into the box, and then that auto generates an analysis. So if we click on project owner, the financial analysis for project owner provides information such as normal costs, normal revenue payments, equipment, ongoing maintenance, and the payback period. It also gives a funding model. On the right, we have the net present value, cumulative net benefits, and the IRR. So of course, each stakeholder will have different financial interests, and the tool allows you to select the stakeholder type to view information that's relevant to them. So if we change this to the site developer, for example, they might not be interested in payback, but instead might want to know the income from the project and ongoing OpEx. So by giving various views on the design, this ensures that the council, the design consultant, the developer can all come together on the tool and have a common understanding. This will ensure that the proposed design is more likely to receive stakeholder buy-in and will importantly reduce the number of iterations needed to suit stakeholder requirements. So any iterations that are required can be produced very quickly due to the automated process. So that makes it no longer very time-consuming to make small changes to the network. Other tabs include the sensitivity analysis. So this tells you which elements in the model that the business case is most sensitive to. So for example, in this case, the total benefit is 17.8 million. And we can see that if the price is reduced by 5% and the demand is reduced by 10%, the total benefit is 15.3 million. We can also see how build and operate cost fluctuations can affect the business case, and also how the benefits and costs interact. Within the energy balance profile, we have the logical design of the main heat source. So this tells us what the network's delta T value is. There is an overview of the pipe design, including the heat conductivity and material diameters, etc. Within route design, we have the length of the pipe, and you'll also be able to switch between distance between pipes and junctions, and then the energy flows between those pipes. If I click log out to return the presentation, so So within the process, we then tested the outputs and functionality of the underlying tool and the user interface against our question of how can we increase the number of studies conducted, and how can we increase the number of studies that progress to build, and how can this, be sufficient to scale up district heating deployment. So we want to question, have we addressed the user's pain points, and have we removed the barriers? Now, we found that compared to existing methods, the users estimated that our tool's process automation will speed up feasibility studies by 50 to 70% and reduce the cost of the studies. This will enable more feasibility studies to be conducted per year. And they said that the automation also will educate and enable less experienced users to test the feasibility of networks. So this opens feasibility studies up and partially mitigates concerns over skill shortages. The users said also that our optimization and extensive exploration of the solution space is very likely to improve solution design. In turn, this will reduce the number of iterations required, and by optimizing the designs, more designs will be viable and more feasibility studies will therefore progress to build. Importantly, the tool is suitable for developing 4th and 5th generation networks, which is something that existing Excel-based modeling has trouble doing. So by building the designs around all the stakeholder KPIs in the first instance, the users expect there will be an increased stakeholder buy-in and less perceived risk, resulting in more capital availability. The users expect to avoid all of the current back and forth needed to get the designs just right. And because the flexibility for stakeholder desires is built into the tool, tweaks to the design can be implemented so quickly that unavoidable changes in spec will no longer delay the process by weeks. So what next? So we have 3 key steps that we need to achieve in the beta phase, which will take all the learnings from the feasibility study to the next step. So firstly, we want to develop the application to a commercial quality level so that we can deliver service to the market. The aim is to develop it to at least a technology readiness level of 8, but there is potential for us to reach a TRL of 9. Tomorrow we're speaking to our first organic customer inquiry for the project. It's a council who are planning to commission a traditional feasibility study solution for expanding an existing heat network and also retrofitting it with renewable generation. So they were going to go down the traditional route, but after catching wind of our project, they would like to discuss the possibility of using the tool to do this instead. Secondly, we will continue with our user-centric approach and extensively test the application through private and public beta so that we release a quality product that delivers the value stream. We already have a fantastic partner on board for testing as well. And number 3, we will ensure that the solutions that are created by the AI are fit for purpose in the real world. And we will test against industry benchmarks and further enhance the route to market planning. So this concludes our presentation, other than to say a heartfelt thank you to all the stakeholders listening that so generously offered their time and contributed to shaping this research into the exciting project it's turned out to be. City Science's Lee Stokes and James Lewis will be joining me for the Q&A. So if anyone has any questions, we would love to hear from you now. If you're watching the recording and have questions or would like to be involved in the project, please send us an email to info@cityscience.com. Thank you very much for listening.
Brilliant. Thank you very much, Jade. That's very good. So we've got a lot of questions in the chat, so I'll just run through some of them. What are your assumptions about the source of heat used within a network? Do you have to choose from a catalogue? Do you consider waste heat? And if so, how do you handle the uncertainty of its availability through the life of the network?
Yeah, so I'll take this question. So heat demand mapping.
Oh, Lee, sorry, I think we're struggling to hear you.
Hear me now?
Yes.
You better? Yeah, okay.
Yeah.
So heat demand modeling is a big problem, and it's one of the key pain points we pulled out of the process. I think, so the first question is, yes, we will consider waste heat. So that's a key consideration and will be put in. I think the approach we took is to have an iterative approach. So we interface with existing heat demand sources, so tools like Thermos. So Thermos, we actually took all of our data in the first phase from a tool called Thermos. Thermos was Bayes' own modelling tool of choice when we started the project. Since then, Bayes have commissioned a new tool, and that's in the process of being looked at now. In fact, they talked to us about whether we'd like to participate in building that tool. We did decline because we want to focus on this tool. So we've already talked to Bayes about making sure that we've got a common ontology between our tool and the new phase, the new sort of modelling tool that they come up with. So zoning and modelling data will be our first sort of port of call. We then obviously allow the ability to take granular half-hour data into the tool. We're also going to build a capability where you can pick from building archetypes. So you can say, you know, I've got a building of this type and these CIBSE type modelling type archetypes, and we will start off with the CIBSE and then refine them as we go through based on location and region, stuff like that. Finally, the final point about demand modelling is that we have a tool which we again developed in conjunction with Bayes called SMETA, a thermal modelling tool. So SMETA can be installed in a representative number of sites or in all sites as we get later on in the demand process, and to take actual real world measurements of the demand, the thermal demand in the building, and also the thermal losses in the building. So we've got a sort of iterative approach where we can build up from a very poor data set, which is where most people start, and then as the data comes in, we can build that model up.
Okay, brilliant, thank you. So I guess related question to some extent. So can you describe how your heat demand source data and the assumptions behind it?
Yes, I mean, there's no magic in our heat demand source data, right? It's the same as everybody else's. We've got the same problems as everybody else who does this, right? So heat demand, you take an initial snapshot, so 2 years worth of heat demand, and then you have to forecast based on the buildings and the likely profile of the buildings over the 2 years, whether that's going up, whether it's going down. And we also forecast the prices, obviously, of what's going on with the market prices of the commodity underneath. So there's no AI magic under that model. It's the same as everybody else does on every heat project per day. SMETA is a bit of a game changer because we can actually take real world measurements, which currently doesn't get done. So the best you probably get to today in a traditional tool is you get half-hour data from the buildings. We probably will go just one step further than that, putting actual measurements into the building.
Right, thank you. That's fantastic. So there's been a question about what is the price point for customers? Is it a price per seat or a price per project? So this is obviously for your commercial users of the tool.
Yeah, so if we sell this tool as licensed, so you can buy the tool off us as a licensed product. We benchmarked it against other products in the market, so like Comsoft and the like. The tool price point will be 8,000 per person per annum, which is along the same lines as all the other tools. So then Comsoft is 8,000 euros, but they're all in that sort of price range. So we're competitive with the market pricing.
Okay, great, thank you. How does your modelling determine network routes for heat pipes, or does your modelling determine network route for heat pipes? And if so, how does it do it?
It does. So actually, City Science a transport consultancy company, one of its arms. So we've got a lot of experience planning routes for transport. So we actually follow some similar sort of logic that we do with transport. So Steiner models or traveling salesmen, there's modifications of these approaches we use to transport from transport in network design. The only real difference between what you're doing transport and what you're doing routes for networks is the difference between what ground you're going through. So it's much more expensive to go through a hard big piece of ground than it is to go through a soft big piece of ground. So what we've tried to do is we've tried to take that in and sort of factor into the model as well. So rather than choose the most transport efficient route, we've obviously factored in what you're digging through and how much that's going to cost. And then obviously we iterate that as one of the AI routes. So you come up with a basic model based on normal route modeling, and then that's iterated to try and optimize it.
Yeah, if you want me to coming a little further on that one, what we've essentially done is generated signer points around all the dig obstacles on the particular site, and then add those as possible optional edges to the minimum spanning tree to solve. And then you can look at whether it's worth your while to circumvent an obstacle by building longer pipe length but cheaper dig cost, or whether it's just plough through the obstacle, higher dig cost, shorter pipes.
Fantastic. Brilliant. So someone has asked about how does this tool integrate with other tools, Thermos, for example. I believe that's one of the ones that you mentioned in the slides.
Yeah, so we're integrating with Thermos, which, like I say, was the zoning tool of choice when we started the project, and we have a plan, and we've agreed with Bays already that we'll have a common ontology with their new tool we're building. Obviously, we're a beta tester, technical beta tester for Icebreaker 1 as well, so we plan to take data from Icebreaker 1 into our tool to consume as a sort of data layers, but we also plan to publish into Icebreaker 1 the output from our data. So any heat modeling data and greater granularity maps that we have, we're going to publish into Icebreaker 1 so everyone can take advantage of them. So that's one way. We've also teamed up with another MedApps 1 partner called Advanced Infrastructure. They are doing something aligned to us, but on the energy side. So they're modeling energy networks. And if we both get through to phase 2, we plan to integrate with them as well. So we'll have a combined energy and heat modeling approach that's common across the two, which will hopefully help us expand the UK infrastructure outwards, because heat and energy are both critical, as you heard in the last presentation for the UK infrastructure.
Great, thank you. And in terms of your engagement with Icebreaker 1, so picking up on one of the other questions from the previous slide, what's your engagement been with the Icebreaker 1 and Open Energy project? Have you been technically on the beta program, or have you just been kind of early stage discussions?
No, we've been both. We've had several conversations with them about common data standards, how we approach it, the interfaces. We've already defined for our beta spec, and James might be able to tell you more about the spec of it. But we've already defined an interface and how we'll interface with them. We're part of that technical beta that's going on at the moment, so we're not just talking to them, we're using code to allow us to interface with them directly.
Great, thank you. So there's a bit of a challenging question here, perhaps. So someone has asked, so your solution tackles 6 of the 13 main pain points, as Jade described. So how are the other 7 being tackled, and does tackling 6 actually unlock the value you are targeting?
Yeah, so the value proposition is built off them 6. So there are pain points in the process, which we just accept, right? So a valid approach to risk management is you accept the risk you cannot change. So, and to give you an example, so an example of one of the risks we're not going to fix, right? So each project currently today that's built from a big major heat network is a bespoke project. It's completely bespoke, it's done standalone, the contract in terms is bespoke, the timescales are bespoke. And this was brought up as one of the risk points, that there's no cross-validation across projects, and there's no learning that's propagated throughout the process. It's basically all held within the project. So this is a risk that, unless we take the whole market share and we learn, it's just a risk that we have to accept. But we understand that it is a key risk in the process, and if we can address any small outlying edges of that risk as we progress through, we will. But we just understand that it's an inherent risk. The same as, I think, one of the questions in the text was, how do we fix the future demand problem? So demand could tail off for the problem. Again, it's just an inherent risk. We'll try to model that as best we can, the same as every other design consultancy does. But can you truly know the future? Not really. It's an inherent risk that we all have to live with, right? And we have to take a view on the risk of that. So the way we plan to manage that is, we can't fix the risk, but we've designed in the system the sensitivity on the business case, and we also have an error propagation algorithm that takes the errors that could be at the beginning of the process, like demand risk, and propagates them all the way through to the end. So we've tried to manage that risk out, but again, it's just a risk we accept and is inherent in the process.
Brilliant, thank you. That's great. And then in the last minute, I've got one final question, but if anyone else has anything they want to add on the chat, then please do. So you mentioned about the challenge of each project is very separate and individual, but you also mentioned that you've been talking to Bays about ontologies. So do you see any potential for kind of a shared ontology approach to help reduce the kind of islanded nature of each of the projects?
Yeah, absolutely. So the two big problems, right? So and where it's all bespoke is the data that goes into the tool. So working with Bays, we 100% think we're going to be able to address some of that. It's not in our value proposition, but we 100% think as we go through working with Bays, common ontology, interfacing with tools like Thermos, and whatever comes next, because Thermos won't be the tool of choice soon. Yeah, we 100% think an open UK, a UK-wide architecture for data is the right thing to do. Like that will address some of the problems, 100%. It won't address all the problems in terms of things like bespoke contract terms and that sort of stuff. Although Bays have done work in that area trying to come up with bespoke, standard contracts like ESCO, a standard ESCO contract for heat network provisioning. But I don't think we'll go that far. But certainly the open architecture point of view is something the UK sorely needs, and we definitely think we're a part of that.
Okay, brilliant. Thank you very much. I think that's it for questions. If you have any final closing remarks you want to make, then feel free.
Just thank you. And sorry, my mic's so terrible. I'm sitting forward.
No worries. It's fine. Brilliant. Well, thank you very much for everyone for contributing on the questions, and thank you to City Science for your presentation and Q&A. We now have a short break again before the next presentation. So we'll be rejoining at 11:30 to go through Brits Energy proposal. So thank you very much.